In this problem, we're trying to find the steady state solution to this 2 degree of freedom system. Now, we're given a lot of the information here, so we are going to see that it is a simple harmonic forced 2 degree of freedom system, and we're just looking for the steady state response here. So we want to find what I will call x steady state of t, where this x vector is going to be made of our 2 degrees of freedom. I'll be calling x1 and x2. So we'll start with our modeling step, although really it's completely done for us. We're going to have our mass matrix in base units, 1002 kilograms. I'll just recopy this information. We have a stiffness matrix in base units, 5, -2, -2, 3. That's newtons per meter. And we have a damping matrix now. And again, in base units, we're given it's 4, -1, -1, 2, and newton seconds per meter. Looking at these given matrices, they are all symmetric, which is going to be a rule for all of these linear systems. So that's good so far. And then on the forcing side, in base units, the force amplitude vector is 1, 2, and our driving frequency is going to be 3 radians per second. So we can quickly put these all together and establish our equation of motion, and we already know what form the system is going to be in. So in general, the equation of motion is going to be our mx double dot plus cx dot plus kx equals, and we're told that this has simple harmonic forcing, so it's going to be this f cosine omega t. So in this case, the 2 degrees of freedom are each affected by a forcing, 1 newton and 2 newtons of amplitude respectively, both at the same frequency, the 3 radians per second, and they are in phase with each other. So specifically for ours, our equation of motion numerically will copy in here, plus our damping matrix for -1, -1, 2, and the stiffness matrix, 5, -2, -2, 3, x, and that's 1, 2, cosine 3t. And everything is in base units here, newtons, kilograms, meters, seconds. So for this problem, the modeling step, the equation of motion step, is pretty trivial since we're given so much of the information. Usually that will be more to handle. We'll have to use Lagrange's equations to get those MC and K matrices. But now we can identify what system we have. So it's 2 degrees of freedom since we have all these 2 by 2 matrices. It's linear. We were able to put everything in matrix form and put it in the standard format. We have simple harmonic forcing on the right-hand side. And beyond that, every degree of freedom has the same frequency and phase. And we have damping in our system. It's not going to be too crucial for how we are going to be solving this since we're only looking at the steady state solution, but it is a damped system, so we have damping. All right, so we are looking for just back in the find, just the steady state solution. So we know that when this is the case, 2 degrees of freedom, linear systems with simple harmonic forcing, our steady state solution is going to generally be in the form of this x cosine omega t. So omega, we know that's the driving frequency, 3 radians per second. So it's this x that we are going to need to figure out. And we're going to do that in the parameters step. So for these types of systems, our x is going to be equal to this z matrix, our impedance matrix, inverse, times our force amplitude vector f. So we need to calculate this z matrix, the impedance matrix, and that is going to be defined as the k matrix plus j omega times the c matrix minus omega squared times the mass matrix. So notice here, this is using omega, the driving frequency. The natural frequency actually does not really come into play here directly. We don't need to calculate it. I mean, it's going to come into play in that it's a function of the natural frequencies are a function of the mass and the stiffness matrices, but we're not directly calculating it in order to find the steady state response. Because we're only looking at the steady state, the transient or the homogeneous part has already died off by now. That's affected by our natural frequencies. The steady state is only affected, at least frequency-wise, by the driving frequency. So for now, we can calculate Z by hand using the K, C, and M matrices, which we already calculated above. So that is going to be the stiffness matrix, 5, -2, and 3. Plus 3J times 3, the driving frequency, times our damping matrix, 4, -1, and 2. Minus 3 squared times the mass matrix, which is 1, 0, 0, 2. Carrying through this calculation, we get the complex values in our matrix, -4 plus 12J, minus 2 minus 3J, minus 2 minus 3J, it's still a symmetric matrix, and minus 15 plus 6J. So that's our impedance matrix. It's complex because we have damping in this system. Again, we can also do this for undamped systems, and Z is going to come out to be real, purely real, so we're not going to have to go through this next step in a moment where we're going to find magnitude and angle. But in this case, we do have damping, but we can carry on because now we can calculate X, because it's going to be Z inverse times F. So we're ready for that calculation. So X equals Z inverse times F, which again, that was in our equation of motion, is 1, 2, the amplitude of our forcing. So I'm not going to rewrite Z. Now, to invert a 2 by 2 matrix, we can do that by hand. It's not too bad because we have a shortcut to do so. However, it is complex, so that's just going to add some difficulty to doing it. So for this calculation, I'm going to let MATLAB do the calculation for us instead of trying to do this by hand. So I'm going to invert Z and then multiply it by this 1, 2 vector to find X. Jumping into the MATLAB, I'll put in all of those given parameters and replicate everything I've been doing so far by hand here. And I'll let it calculate Z and see that we get that same Z that we just saw. So this is now where we are at by hand. We're doing Z inverse times F, which I'm doing in 204. So remember, in MATLAB, it's generally faster to, instead of doing something inverse times a vector, to use the backslash operator, and that's what I'm doing here. So Z backslash F is essentially going to be the same as Z inverse times F, and I'll show that in a moment. It's just that MATLAB will generally do a backslash faster than it will do an actually inversion of the matrix. But let's see what happens. I can do inverse Z, and it inverts the matrix for me, and that's fine. And I'm going to do inverse Z times F, and we see that that's the result we get. I'll copy that down in a moment. But if we do the same operation here essentially, but with the backslash, let's just see that we do get the same result. Now, for a 2 by 2 matrix, we're not really going to see a difference in speed, but as we go into multi-degree of freedom systems in the next section, we see an increase in speed using the backslash operator. And since the procedure is, we're going to see essentially the same as we go to more than 2 degrees of freedom, as we're seeing here, we will see an appreciable speed up in these larger scale systems by using that backslash versus actually inverting the matrix first. Also another note here, when I'm defining Z in 201, for that J omega times C, I do have here omega, or I'm calling it W here, times 1J times C. So 1J in MATLAB is a little bit more reliable since it is possible to assign a value to J. It will think it's a variable. If I have 1J or 1I, it knows that I'm talking about the square root of -1. So it knows what that is, or if I put 1I, it knows what that is. So one more time, let's look at what that X is. And we see it down here. This is the x vector. It is complex, as we expect, because z is complex, because we have a non-zero damping matrix. I'll copy down what we got out of MATLAB, although a lot of this we'll keep doing numerically. So we get negative 0.0538 minus 0.0527 j for the first row, for the first element, and negative 0.124 minus 0.0318 j for that second element. All right, so that is that x matrix, or x vector in this case. And if we see, that is going to be the coefficients in front of the cosine term that gives us the steady state solution for the first degree of freedom and the second degree of freedom. So we are faced with this issue here that x is complex, and physically that's not going to make any sense to us. So what we need to do is convert these complex kind of Cartesian form values into polar values, a magnitude and an angle. So what I want to find is what I will call x1. I'll just use a superscript, but that's just talking about the first degree of freedom. And x2, the second degree of freedom. And I want their phases, I'll call phi1 and phi2. So again, this is just going to come from complex algebra, finding the angle of each of these entries for phi and the magnitude of each of these entries for the x values. Returning to MATLAB for this step, the magnitude, we can use the ABS, or absolute. So let's first see what it is. If I do absolute value of x, I'll start with this. It's going to give me the absolute value of each element in this vector. So let's just see again quickly, what is it doing? I'll just do it for the first entry. It's taking the square root of the sum of the squares of the elements. So for the first entry here, that is going to be 0.0538 squared plus 0.0527 squared, and the square root of that. So notice I dropped the negatives because I'm squaring the coefficients anyway, and we get 0.0753, and that's exactly the first entry for when we do ABSX. So that is all the absolute value is doing, is it's finding the magnitude of each of the elements of x. Now, how do we find the angle? What's the angle function actually doing? Well, it is going to be finding the angle using the vertical component and the horizontal component. So again, let's look at what the answer is when we use angle. And notice this is going to be in radians. So if I take the angle of this x vector, this is what I'm getting. And how is it computing that? Well, we can use atan2 here. And we can put the y component, or the vertical component. That is the coefficient of the imaginary part. So let me again do this for just the first element of x. So negative 0.0527. Negative 0.0527. And here the negative is going to be important. And then x, the horizontal or the real part, also important that we include its sign, 0.0538. Going back up here, negative 0.0538. And when we do that calculation, now notice there's a little bit of rounding since I'm only taking 3 digits in this atan2, so that's why I'm getting negative 2.3665. But when I just did angle of x, I get a little bit of a different value because there was values in here not being reported. So I'm getting basically the same values both ways, but angle, that is what it's doing in the background, is taking the 4-quadrant arctangent of the imaginary coefficient over the real coefficient, and that's how I'm going to find phi and x. So doing this again all together now, we have the magnitudes for each of the steady states and now the phase for each of the steady states. So writing down what we have, the first magnitude 0.0753 and the second magnitude 0.128. The first phase, we get negative, I'll just keep 3 digits here, negative 2.37 radians, and the second, negative 2.89 radians. So now we can put our entire answer together. I don't need initial conditions here because I'm only looking at the steady state solution, so I'm skipping that initial condition step, it will only affect the transients. So this means that my x steady state of t is going to be, now I can express this in matrix or vector form here, 0.753, 0.128 cosine of 3t, they both have that same frequency, plus, and now the phases, that is going to be different for the first degree of freedom versus the second. All right, so that's one way. So the first row is x1 and the second row is x2. This is my steady state solution for those 2 degrees of freedom then. So different amplitudes, the same frequency at steady state, and different phases. So let's see what this looks like when we plot it. What are the responses going to be? Back in the MATLAB, I am going to assemble my solutions with these inline functions just as I have them written before. So x1 and x2 I'm going to define separately for the first element of the amplitude and the first element of the phase, and then the second and the second. And I'm just going to plot them, and I'll do this just for 4 forcing cycles. So the forcing cycle is based on my driving frequency omega. So I will plot this. And this is what we get for the response, x1 in red, x2 in blue. So notice the amplitude or the magnitude of blue is higher, which should be expected, as its amplitude is 0.128 versus 0.075 for the red, and that's what it's hitting here. And they are not quite in phase with each other, which should not be, we should not expect that, as those phi values were a little bit different. They're pretty close, but their peaks are not lining up. And we see at steady state that they are indeed only oscillating at that one frequency, which is the driving frequency. And finally, we can look at a little animation of what they're doing when they are at steady state. So we see, if we run it one more time, not quite in phase with each other. Their peaks, their valleys don't quite align, but we see that they are oscillating at that single frequency of 3 radians per second. We got that closed form steady state solution by starting at the modeling step, which in this case we were given really all the information we needed, assembled our equation of motion, and notice that in this case our right-hand side was the simple harmonic forcing, the same frequency and phase acting on all of our degrees of freedom, which allowed us to know what the steady state solution was going to look like, this x vector times cosine omega t. If our forcing was more complicated with different frequencies, different phases, we would not be able to use this form of the solution. But here we can. So in this form, we can find that impedance matrix by calculating it using the M, the C, the K matrices. Z is, in this case, complex because C is not a zero matrix. We do have damping here. Z being complex then means that that X vector is complex as well. So what we do to address that is, instead of trying to plot with complex variables, which don't make physical sense, we take X, we find for each element its magnitude or its absolute value and its angle using the 4-quadrant arctangent or simply the angle function in MATLAB, giving us the same results. Then we can assemble our entire solution using the magnitude times the cosine for x1 and x2, and then the phase is going to come from the phi1 and the phi2, and that gives us that steady state solution.